This video is about oxidation-reduction reactions, which are often called redox reactions. So we've talked about acid-base reactions, and redox reactions are kind of the opposite. Instead of transferring a proton, they're transferring an electron, or often more than one electron. So redox stands for simply reduction oxidation, it's just shorthand. So there's always something, just like acid-base, where you have to have an acid and a base. There's always something being oxidized and something being reduced. The thing that is being reduced is the one that's gaining an electron, and it is called the oxidizing agent because it's causing something else to be oxidized. The thing that's getting oxidized is losing an electron, and it's called the reducing agent. A little bit more on that later. So if we have an example reaction like this, so we have zinc metal, copper ions, and then that's going to become zinc ions and copper metal. So what's happening is we're transferring some electrons from zinc to copper. Okay, the zinc is going to lose 2 electrons, the copper is going to gain them. We can see this if we write the half reactions out. So the half reactions show the electrons. So the reduction half reaction would be the copper gaining the electron to become copper solid. The oxidation half reaction would be zinc losing its electrons to become zinc ions. Just want to be really clear, half reactions cannot happen on their own. We can't have electrons just floating around willy-nilly by themselves. They have to go on to something, so we always have to have a half reaction that's reduction matched up with a half reaction that's oxidation, but sometimes it can be helpful to write them out separately for us to look at them. Some acronyms that can help you. There's 2 of them, and sometimes I find them actually both useful in different situations. So the first one is that Leo goes grr, like a lion. So if you're losing electrons, that means it's oxidation. If you're gaining electrons, it's reduction. The other one is oil rig, which states that oxidation is losing, reduction is gaining. I honestly find these helpful depending on what I know and what I'm trying to figure out. So if I know that something is being oxidized and I'm like, is that losing or is that gaining? I use oil rig. If I know something's losing electrons and I'm trying to remember, is it oxidation or reduction? I use the Leo goes grr. So both useful in their own way. So the last example with the ions, pretty obvious to tell what's going on. Sometimes it's not as easy. So combustion reactions, like this one, this is burning methane gas, is actually a redox reaction. But if you look at that, you're probably like, where are the electrons going? I don't see any electrons. I don't see any ions being formed. It's not as obvious, okay, because they're being transferred in the process of covalent compounds. We use something called oxidation numbers or oxidation states to help us tell where those electrons are going. So again, these are most helpful in covalent compounds. We can determine the oxidation state of ions, but generally you don't necessarily need to. You can just see it. So the oxidation number is the charge an atom would have if it were ionic. Okay, so if methane was an ionic compound between carbon and hydrogen, where we're literally transferring electrons, which one would be positive, which one would be negative? What would the signs on that be? Okay, I just want to be really clear, they are of course not ionic. Okay, they do not actually have these charges. This is a bookkeeping method. It's not really based necessarily in reality. It is based on something that is easy for us to know. Okay, so some general guidelines for determining these oxidation numbers. First of all, any element in its elemental form is 0. So for metals, this would be the solid, sodium solid, iron solid, whatever. For most nonmetals, it's actually a diatomic gas. So we know oxygen is found not as just oxygen atoms floating around. It's O2, Cl2, etc. So those have 0 oxidation states. And we can kind of see why that had to be the case, because also the oxidation numbers of a compound must sum to the total charge on the compound. Okay, so for sodium solid, the only way that's 0 is if sodium is 0. Okay, for something like O2, I guess you could think maybe one O is negative and one is positive, but that doesn't make any sense. Why would we choose one or the other? So instead, they're just 0. And then I'm going to give you another set of rules. They follow an order of importance, and so the rules are only superseded by the ones above it. However, probably 98% of the time, you don't really need to know what order they're in if you simply remember the 5 or 6 rules I'm about to give you. And it only becomes a problem what order if they counteract each other. But most of the time they don't. Okay, so the first rule is that elements are 0. Already got that one, great. The second rule is that fluorine is -1. Okay, so these oxidation rules do come from reality. They come from the fact that more electronegative atoms are going to be the ones that are going to be negative, so fluorine being the most electronegative thing on the periodic table. Anytime it's bound to anything else, it would be the one to take the electrons. Okay, exception, of course, would be if it's an element. The third rule is that the group 1A and 2A metals are +1 and +2 respectively. This is the charge we expect them to be if they actually are ions, so that makes sense. Of course, unless they're elements. Hydrogen is +1. Again, unless it's hydrogen, the element, or there are occasionally things like NaH, kind of a weird compound, but in that case it has to be -1 because rule 3 supersedes it. But again, that's going to be very uncommon. Most of the time, you can simply say H is +1 and move on. O is -2. You can these last two also, if H is in something like a compound we consider to be ionic, it would be +1. If O is in something we consider to be ionic, it would be -2. So these numbers don't come from nowhere. Exceptions, of course, if it's O2 or if it's with fluorine. Fluorine is going to supersede that. Again, reasonably rare. Then the rest of the halogens show up. Fluorine we already took care of, okay? But the rest of the halogens also like to be -1. They just don't like to be -1 as much as fluorine. So again, unless it's an element, or with fluorine, or oxygen is the big one. So that's actually why this is below O, is so that it can be, oxygen can supersede it. And then all the other elements are assigned so the charge is sum. So really, we have the halogens being -1. We got H being +1. We got O being -2. We're honestly not going to see the metals very often. So that's really it. If you know those rules right there, unless they counteract each other, you don't need to worry about the order. Okay, so there's this helpful circle squares method just to make sure that you're actually keeping track of the actual oxidation state. So the oxidation state on oxygen here is going to be -2. However, there's 2 of them, so the total negative charge that you could think of coming from the oxygen is actually -4, which means sulfur, to balance that out, has to be +4. Okay. However, if I ask you for the oxidation state of oxygen, I want -2, not -4. So this is just a helpful little thing that helps some people. So you draw a circle under each element and a square under that. In the circles go the actual oxidation states, the oxidation state on each individual atom. And in the squares, so we got the -2 for oxygen, that's part of our rules. In the squares, we write the total oxidation number for all of that type of atom. So basically, it's the number in the circle times the subscript. So in the square under O, we should write -4. This is not the oxidation state of oxygen. Okay, it's just the sum, so that we can try to help figure out what S is. Then the sum of the squares is what must sum to the total charge, not the circles. So that's what the squares are for. It's for determining the total charge. So that means that S has to be +4 in the square. There's only one S, so it also has to be +4 in the circle. So that's how we do it. So basically, we just figured out the oxidation states of sulfur. I'm going to do one more example. This one has 3 in it. So what are the oxidation numbers of the elements in HNO3, nitric acid? We'll write our circles and our squares. Step 1 is going down the rules in order, and again, I just want to clarify, it's not even that important if you don't go in order. But there's no elements, there's no F, there's no metals. H is +1, so we'll put a +1 there. There's only one H, so +1 also goes there. O is -2, and because we still got nitrogen to play with, the hydrogen rule does nothing to this to be a problem. So O is -2, there are 3 of them, so -6. Step 3 is then determining the remaining. There should only be one thing. Okay, if there's more than one, well, what are we going to do? But there should only be one thing that does not fit into the rules. So that the sum of the boxes has to equal 0 because the charge on nitric acid is 0. So that has to be plus 5. There's only one nitrogen, so that has to be plus 5. So the oxidation state of nitrogen is plus 5. So the answer, if I asked for the oxidation numbers, you would want to give me plus 1, plus 5, or minus 2. If you use my little circle squares system, I know that you mean your answers are the circles. If you do not use this system, you better be careful, because if you just write the squares, you will get it wrong. Okay, so either use the system or be very explicit in what you're trying to state that the answer is. All right, so in the reactions then, we can use the oxidation states to determine what's getting oxidized and reduced. So here's our combustion reaction again. I'm going to not use the circle squares method. I'm just going to, in my head, basically use those squares. I'm going to determine the oxidation numbers. Okay, so H is plus 1, but there's 4 of them, so that makes the C minus 4. The O is an element, so it's 0. In CO2, O is minus 2. There's 2 of them, so C is plus 4. In water, H is plus 1. O wants to be minus 2, which actually conveniently works out perfectly. So in water, the hydrogen and the oxygen rules work out perfectly. So we've got that. So now, if the number decreases, it gets reduced. That's what the reduce, we are reducing the oxidation number. So we can see that oxygen goes from 0 to minus 2. That's a reduction, so it's getting reduced. Anything that increases gets oxidized. So we can see C goes from minus 4 all the way up to plus 4. And so it's getting oxidized. We can see here that hydrogen does not change in this reaction. Okay. It stays plus 1, so it's getting neither oxidized or reduced. Very frequently in things with more than 2 types of elements, you will see that most of the things don't change. So essentially what we've done, we've transferred some electrons from the carbon to the oxygen, even though you don't see the charge change. Okay, so back to, remember I mentioned we can actually call things reducing and oxidizing agents. So a reducing agent is what gets reduced, is what gets oxidized because it's causing something else to be reduced, and an oxidizing agent is what's getting reduced. Convention here is that we write them as the entire compound as the oxidizing agent, whereas we might say that in a specific element is getting oxidized. So in that combustion reaction, the carbon was getting oxidized, the oxygen was getting reduced. So the oxidizing agent was O2, and the reducing agent was CH4, not just C. Okay. The last little thing on redox is learning how to balance them. So the key on redox reactions is we actually have to balance the electrons as well as the number of atoms. You can also think about this as balancing the charge on each side of the arrow. So if we look at this reaction, it may look balanced to you because we only have 1 chromium on each side and we have 1 nickel on each side, but the electrons are not balanced, and we can see that by the fact that we have a plus 2 charge on the left and a plus 3 charge on the right. So somewhere an electron got lost, it's not balanced. So a couple of different ways to balance here. The first one is called balancing by half reactions. So what we do here is we simply separate them into the reduction and oxidation half reactions, balance the elements if necessary, and then we add electrons to equal out the charge. Generally pretty simple to see when we have ions like this. So the reduction half reaction is nickel 2 plus going to nickel, so we need 2 electrons to make that work. The oxidation is chromium going to chromium 3 plus. We lose 3 electrons to make that work. You can also think about it as the 2 plus of the nickel needs to balance out with the 2 minuses of 2 electrons, so charge balances. Then we need to multiply each by some number so that the number of electrons in the 2 halves is equal so that the electrons cancel. Okay, we can't have electrons floating around on their own, so they have to cancel out. So notice that the reduction will always have an electron or one or more than electrons in the reactants. Oxidations will always have electrons as the products, so they will cancel as long as they're the same number. In this case, this is probably the hardest one because we have 2 and 3. So we have to multiply the top reaction by 3, bottom reaction by 2. We now have 6 electrons on each side. Now we add them up, the electrons cancel out, and we end up seeing that we need 2 chromiums for every 3 nickel ions. Okay, another way we can do this works on simple reactions, is what we're going to be doing this term. You will see more complicated reactions next term, is simply to add the spectator ions. This essentially causes you to balance the charges. So instead of doing that, what you just do is throw chloride in there. It can be any anion. It doesn't have to be chloride. You can use fluoride if you like that. I don't care. To each cation, so that you balance out the charges. So to nickel 2+, you add 2 chlorides. To chromium 3+, you add 3 chlorides. And now we simply balance it like it's a normal reaction, which you know how to do. We're going to have to put a 3 in front of the nickel 2 chloride and a 2 in front of the chromium 3 chloride. And, balance accordingly. And then we simply remove the chlorides. So either way, you'll get to the same answer. If one works better for you, you do it that way. When you do get to the more complex reactions, you do have to do it using the half reactions. So good idea to try them right now. But if you're on a test or something and you're like, oh gosh, that seems overwhelming, throw those spectator ions in and do it that way. And this is the end of this video.